In this interactivity, we're going to study the factors affecting the force on a wire. What happens if you double either the current or the flux density? By moving the relevant slider to the far left. So first, let's see what happens if we double the current by moving it one step to the left. So we double the value and the balance displays 2 grams instead of 1 gram. However, if we doubled the flux density, the balance displays 2 grams instead of 1 gram. So the magnetic assembly moves downwards and the balanced reading doubles to 2 grams if we neither double the flux density nor the current. What happens if you double both the current or the flux density? So let's double the flux density and the current. What do you notice? Yes, the magnetic assembly moves downwards further and the reading quadruples from its original value, which is 1 gram, to the display value of 4 grams. Now let's select long length to double the length of the wire. What happens when the length of the wire is doubled? Exactly. The reading on the balance doubles again to 8 grams. We can see that by doubling the flux density, the current I, or the wire length L, doubles the force F on the wire. So we say that F is proportional to each of these quantities. These quantities are related by the equation F equals B multiplied by I multiplied by the length. Therefore, B, which is the flux density, equals to the force divided by the current multiplied by the length. F divided by IL. So, if 1 meter wire carrying a current of 1 amperes in a magnetic field experiences a force of 10 newtons, it must be perpendicular to a magnetic field of flux density 1 Tesla. This gives us the definition of flux density and Tesla.